Welcome to Dr. BT's Chemistry Essentials, A-level chemistry made easy. In this video, we're going to be looking at carboxylic acids. We're going to be looking at the reactions that they undergo, some things about naming them, and then looking at their water solubility. So carboxylic acids belong to the family of carbonyl or acyl compounds, and they have this C double bond O, and they have an X group, and this X group be any number of different groups. So if it's hydrogen, it's an aldehyde. We've got ketones, esters. Obviously, carboxylic acid is what we're focusing on today. But related to carboxylic acid, there is the acid chloride and the acid anhydrides. So you substitute this X for any of these groups, you get these different acyl carbonyl containing compounds. So, as I said, we're going to be looking at carboxylic acids. We're going to be looking at their chemistry. The carboxylic acid that contains all of these groups of atoms together. So we're first going to be looking at the idea of how to name a carboxylic acid. You name a carboxylic acid by looking at the alkane or the parent alkane and replacing the E at the end of the alkane's name for oic acid. Let's have a look at an example of this. This here has 2 carbons in it, so the parent alkane is ethane. It's obviously 1 carbon methane or meth, 2 carbons eth. And what we do is we take this E and we replace it for the oic acid. That's exactly how we get the names of these carboxylic acids. Thing to note with naming a carboxylic acid is that the carbon of the carbonyl is always designated as 1. It takes priority over everything else. If we were to actually number this carbon, this would be 1 instead of 2. Let's put this in practice with a carboxylic acid with some branching in. Okay, what I'd like you to do now is to try and pause the video here, see if you can name this particular carboxylic acid. Okay, so our longest alkane chain is going from this end all the way through to this end. Start this carbon as carbon 1 because it has top priority. Lead from there. That gives us the name of our parent alkane. So we're pentane. Obviously we have our carboxylic acid as the 1 position, and that changes it, this E, to oic acid. It's worth noting that because carbons of carboxylic acids are always 1, you don't need to put any number here. It just flows into 1. And then we've got branching at positions 2 and 3. It's 2 methyl groups, so it's going to be dimethyl. And we have to designate those numbers. Remember, as we go between numbers and letters, we have to put a hyphen. So we're going to put a hyphen here. And then because we've got 2 sets of numbers, it's a comma. So that's our answer for this. So if you got that, well done. Now we're going to focus on some of the chemistry of carboxylic acids. First thing to mention here is that carboxylic acids are exactly that. They are acidic. They are weak acids because there is partial ionization of this hydrogen to form a carboxylate. If we were to take the simplest carboxylic acid, methanoic acid, and add this to water, it would ionize to form methanoate and a H+ ion. Important to realize that this form of a carboxylic acid is called a carboxylate. For every carboxylic acid, it forms a -1 negative charge. The fact that it's an acid lends itself to explain a lot of its chemistry. Acting as an acid, if it was to react with a metal, then it would follow the MASH acronym. Metal plus acid gives salt plus hydrogen. And you can see here that the sodium plus is 1 positive charge, and we know that the carboxylate formed is negatively charged, so they now balance each other out to form an ionic salt. This one would be called sodium methanoate. Now, things do change if you swap the metal for a metal that is not group 1. So obviously sodium is group 1. Let's switch that for magnesium. Now magnesium forms a 2 plus cation, so Mg2 plus, and our carboxylate is only -1 charge. So we need 2 equivalents of our carboxylate to every 1 magnesium ion. We represent this, so we've got the 2 there, that's easy. Because this is all one species, you have to put brackets around the carboxylate, and to show that you've got 2 of them, you put a subscript 2. And you show clearly the charge on the magnesium ion. Obviously, if this was aluminium, we would then need 3 of these because the ion would be 3 plus. The pattern here is metal plus acid gives salt plus hydrogen. Stated before, this can be memorized by MASH, M-A-S-H. Acids can also react with metal carbonates, such as the sodium carbonate showed here. Carbonates are 2- as their charge, CO3 2-, so we needed 2 Na pluses to balance that. When they react with the carboxylic acid, they are bases. To balance this out, obviously we had 2 sodiums on this side. These will only couple because this is a negative charge, this species here, this is positive, so we need to do this twice. A 2 in front of both of those. And then the other products are carbon dioxide, which comes from the carbonate, and water. And so the pattern for carboxylic acids reacting with metal carbonates is the formation of a salt, shown here, plus carbon dioxide and water. I know this is bad practice because we've got a word equation and symbol equation, but it helps just fit everything in. Okay, the third situation is very similar to a metal carbonate, but this time it's a metal hydrogen carbonate. It reacts in exactly the same way. We form a salt, carbon dioxide, and water as the products. We're going to look at the sodium hydrogen carbonate. This will produce the sodium methanoate salt, and because we've only got Na here, we've got 1 on this side, so that's balanced. So we only need 1 of the carboxylic acids to form that 1 carboxylate. So this is now balanced. And then we've just got carbon dioxide and water. Again, coming from the hydrogen carbonate here and the hydrogen there. So that's the next pattern that you should remember. Carboxylic acids can also react with alkalis, which are soluble bases. An example of that might be sodium hydroxide. That just gives a salt and water as the products. This is our 4th pattern that we have to remember. Again, really aware that obviously in the exam, if they ask you to do a word equation, don't mix up your symbols with those words. Finally, we can take carboxylic acids and react them with a base, like ammonia. The base will abstract that hydrogen there, forming ammonium, and then leave behind the carboxylate. What that means is the carboxylate is attracted to that positive ammonium, and so we form this salt. In this case, this would be called ammonium methanoate. Again, O8 because you're a salt form. So at this point, this table here summarizes some of the key reactivity that carboxylic acids have with metals, metal carbonates, alkalis, ammonium, and metal hydrogen carbonate. So you're best to practice and learn these on flashcards and be able to identify and draw the symbol equations as well. Always being careful that the salt is a carboxylate with either a metal plus ion. If it's a metal 2 plus ion, 2 lots of the carboxylate, or it could be an ammonium ion. So you would always name whatever these salts were ending in O8. For example, if we look at this example, this would be sodium ethanoate. Okay, other chemistry that a carboxylic acid can do is it can be changed into an acyl chloride by reaction with vinyl chloride. It's the byproducts of HCl and SO2 that you need to remember. We've done there, you don't need to know the mechanism for this. We've just switched this hydroxyl group for a chlorine. And then this here, as we'll see in the video on esterification, is more reactive than a carboxylic acid. And therefore, that allows the esterification to happen more easily. The thing it can do is be converted to an ester. This is by reaction with an alcohol. that contains the R2 group here, and also a acid catalyst. As we mentioned earlier, this will be spoken about, this process of esterification, in more detail in the following video. And then finally, a carboxylic acid can also be changed into a acid anhydride. Okay, so lots going on with the chemistry of carboxylic acids. In this video, really, we're focusing in on kind of the naming and the idea of it being an acid and the reactivity here. These three pieces of information about how it can be converted into other acyl groups are going to be picked up in more detail in the next video. So we're just going to clear these three just to simplify it, and then we're going to use this information going forward. Okay, I would recommend pausing the video here and seeing if you can recall all of this information that's on the screen at the moment, because if you can, that's the key knowledge that you'll need to apply to the next couple of exam style questions. Later on in the video, we'll be looking at exactly why carboxylic acids are water soluble when they're short chain. So carry on with some of the questions here until we get to that part. Okay, time to put some of this into practice. So with these four questions here, what I'd like you to do is construct a balanced symbol equation, whether you're given the symbols in 1 or 2, or the words in 3 and 4. And then I also want you to name the salt formed. So pause the video here and have a go at that. Okay, so for question 1, we have ethanoic acid reacting with sodium. So we have metal plus acid, so we know we're going to get a salt and hydrogen as our products. And that salt there is going to be the carboxylate version of the acid with a sodium. Because the charge is completely balanced here, that's absolutely fine. We don't need to do any stoichiometry. And so this is called sodium ethanoate. Okay, question 2, what we've got is methanoic acid reacting with calcium carbonate. So the products we get for that is a salt again, and then we get carbon dioxide from the carbonate section, and then we also get water. Because calcium is a 2+ charge, we need 2 lots of the carboxylate. So we're going to put that in brackets and put a 2 there. And so over here we need 2 there. Ethanoic acid reacting with magnesium. This is a metal plus a acid. The ethanoic acid, we need to use the name of this. So F means we've got 2 carbons. We know the carboxylic acid is always at the end anyway. We've got the magnesium reacting with this. Again, to follow the pattern as in 1, we would have a MASH reaction. So we're going to have salt and hydrogen. Now, just like part 2, magnesium's a group 2 metal, just like calcium's group 2. So the charge on that is Mg2+. So therefore, we need 2 of the ethanoates. And so we put 2 there. The name magnesium ethanoate. Finally, we have propanoic acid reacting with sodium hydrogen carbonate. This follows the same sort of pattern as we have with our metal carbonates. So we're going to form carbon dioxide and water. Propanoic acid is prop, so we know we've got 3 carbons in there. Then we've got sodium hydrogen carbonate. This then forms the salt, sodium propanoate. We also have that carbon dioxide and water. In these cases, the hydrogens of the carboxylic acid have ionized to form the carboxylates, as we spoke about previously, and those hydrogens themselves find themselves trapped in either hydrogen or water, depending on those reactions. So what I'd like you to do is have a look at this typical exam question. I would like you to pause the video here and have a go, see if you can get the answer, and then we'll go through it. Okay, so you can see here we have a carboxylic acid in our molecule, and then we also have an alcohol that won't react with the magnesium, and they've given us a clue here that gas bubbles are seen. You need to know that obviously an acid plus a metal, magnesium, will give you a salt and hydrogen as that gas. Now the equation is going to be making this structure into a shorthand structural formula. So a good approach with this is just to add in any hydrogens, firstly on our skeletal formula, because they're easy to forget otherwise. Just work through the structure systematically and crossing off atoms when you've used it. We've got the OH of that, so we just put that down first. And we've got this carbon here, which is attached to a hydrogen. You've got this R group as a branch, so we're going to put that in a bracket, any branching alkyl groups in brackets. Then we've got this carbon here of the carboxylic acid, so we're going to cross that out. And then the OOH all comes as one, and this is a distinctive formula for carboxylic acids. You can actually draw that simplified version where you collectively put the two oxygens together. We're going to use that formula, react it with magnesium, gives us our salt, magnesium 2 plus cation. So we need 2 lots of the actual carboxylate, and therefore we need 2 lots of this, plus hydrogen as the other byproduct. And this type of reaction is a displacement reaction, because we've been displacing the hydrogen for a magnesium. Okay, here we have another typical exam question. So I want you to pause the video here and come up with the equation for this. Okay, so we've been told that we have sodium stearate as the salt that we are trying to form. It's reacted with sodium hydroxide, so we know this is an alkali. And so we should know that the pattern of reactivity there is the acid, stearic acid, reacts with sodium hydroxide to form a salt and water. We've got a clue here of what the salt looks like, sodium stearate, and we've been given the structure of stearic acid. Use that with our recalled pattern. We know the salt, sodium stearate, is going to be one of the products. Displacement of the hydrogen for the metal. Charges balance here, so that's all good. And then we just have water. Now, because the charge is balanced, we don't have to have 2 lots of the carboxylate for every sodium plus ion. So that will be your 1 marker. Finally, a more synoptic exam question that links to some functional group tests is this one. Have a go at it. Pause the video here, and then we'll go through the answers together. Okay, so in terms of what we've been told in the question, we know it's an aromatic, so it must contain either a benzene or a phenol in. We also have been told that in bromine water, it decolorizes. Now, this is the test for an alkene, so it must have an alkene there. Now, we know that obviously benzene, as we can draw it in the delocalized form, has 3 bonds that are constantly alternating, so you've got 1.5 double bonds. This does not react with bromine to decolorize it, so it must have a alkene in, which isn't part of the aromatic ring, so a C double bond C. So we're thinking that that must be stitching this together, at least on the outside, and it can only be a carbon that is not part of the actual ring, because this form here, that carbon there, has too many bonds around it. And this is all because, obviously, in an aromatic system, the CC bonds are 1.5 equivalent, so they're over the maximum number of bonds carbon can have 4. Here we have 1, 2, 3, 4, plus the actual 0.5 here. So this cannot be the structure. The alkene has to be at least 1 carbon away from the aromatic. We're told that we see effervescence with a metal carbonate is indicative of a acid, because metal carbonate plus acid gives salt, water, and carbon dioxide, which is this fizzing or effervescence. That acid is going to be a carboxylic acid. Acids, again, that carbon of the carboxylic acid has to be outside of the ring. So if we add that in, It can't be inside the ring because the same reasons as we talked about with the alkene bond. So this is our most simplified minimal structure that contains functional group of an alkene, carboxylic acid, and also an aromatic ring. And if we count up those carbons that form part of this structure, you've got 9. And so your answer here is D9. Now this final exam question is going to help us go over a key bit of carboxylic acids, and that's their water solubility. When you look at the structure of a carboxylic acid, its generic structure, you end up with looking at some dipoles that exist in the actual functional group. So obviously oxygen is delta minus, and so the next atom along is going to be delta positive. This means that carboxylic acids are incredibly polar and so have a favourable interaction with other polar molecules. And this means it mixes well with polar molecules such as water. And we can assign this to the structure. This is a property. We can assign this to the structure of the carboxylic acid. We need to add in the lone pairs of electrons that are on the oxygen atoms. Remember, oxygen has 6 electrons because it's in group 6. 1, 2, 3, 4. 5th and 6th are involved in bonds here. And again, 1, 2, 3, 4, 5, 6 involved in these single bonds. We don't show these, but just so that you understand where these diagrams are coming from. When we draw some water molecules, they will favourably interact with the opposite dipoles. So if we add in the dipoles on these water molecules, and also add in those lone pairs on the oxygens, you can see there's a favourable opposite attraction between a delta positive area of the water molecule and the delta negative oxygen and its lone pairs. So we start to build up some intermolecular forces between these. You can see here the angle's correct, and you want to get roughly parallel lines to where the lone pair are extending out when drawing these. So we've got favourable interaction there. This lone pair actually on the oxygen, it can go the other way as well. Goes to the delta positive hydrogen. And then our lone pair on the oxygen here makes a bond to the hydrogen here. Now these interactions only occur between polar atoms, so those with delta minus and delta positive. So if I swap this R1 out for an alkyl group, it's methyl group, making it ethanoic acid that we're looking at, none of these hydrogens have a polarity on them because they're involved in CH bonds. So they will not interact with this, and that's a common mistake. Careful not to draw that in any structures you're being asked to. Thing to note about the alkyl groups is that the longer the alkyl group, the less soluble the carboxylic acid becomes, because the types of intermolecular bonds that alkyl groups do are those London forces or instantaneous dipole induced dipole forces. So what I want you to do here is have a look at this exam question. And whilst it's only worth 1 mark, it is set for high ability students. What I want you to do is look at each of the different molecules, and you are looking for those functional groups that have a polar bonding, and you're looking for the most atoms that are electronegative or electropositive, so the most polar set of atoms that you can see. Pause the video now and have a go at that. Okay, so alcohols are polar, as are carboxylic acids. Selected here. Now, if we put polar symbolism on all of our atoms, actually we have quite few polar areas. Now, the aldehyde here and the aldehyde here, whilst the carbonyl is polar, it cannot undergo hydrogen bonding, and water requires hydrogen bonding to be miscible or soluble in. So those ones that are circled here can undergo hydrogen bonding. So right away, we can see that A only has one site of hydrogen bonding, so that cannot be the answer for the most soluble. So that's C also. C is actually more water soluble than A, and that's because actually you've got an oxygen lone pair on both the carboxylic acid carbonyl and the OH here, and the whole thing can do hydrogen bonding. So C is a bit greater in hydrogen bonding, but it's still not going to be the most. And then here we've got B, where we've got two alcohol groups, and D, we've got an alcohol group followed by a carboxylic acid group. Now D is the answer, and the reason being is that if we think about how many lone pairs there are in D compared to in B, obviously more sites here than there are in B in order for there to be these hydrogen bond interactions to water. So really, in terms of hydrogen bonding, the leaderboard is carboxylic acid wins over an alcohol, which wins over an aldehyde, which wins over a ketone. Obviously these two, we said, because of their polarity and the lone pairs on the oxygen, can undergo some sort of hydrogen bonding. It's not nearly as great as those. So that's something worth remembering. And it links back to the year 1 work that you've done on intermolecular forces and hydrogen bonding. So this concludes this video that has looked at both the reactions of carboxylic acids with metals and bases, and then also we've looked at how carboxylic acids, due to their structure, undergo water solubility as a property. If you found this video useful, ensure that you like it, and then ensure that you subscribe to the channel for new videos as and when they're uploaded.